So I hope everybody's having a good day. We are going to continue with chi-squared today. And we have our next focus activity. I've already posted to the website that the focus activities are going to be due Wednesday of next week after your long weekend. We are going to have one more after this. So there'll be number 7 on Tuesday when you come in. If you know you're not going to be here Tuesday, let me know. I've already got it printed. But you'll be turning in numbers 4, 5, 6, and 7. So at this point, you should have 4, 5, and 6. If you are missing one, we could probably go ahead and look over here and see if there's any additional copies. Hello. Okay. Yeah, you missed it. Oh, what were we talking about? Hello. Okay. All right. Kirtland. Joe. There you go. And that does remind me, does anybody in here not like clowns? Because real close to Halloween, I dress up like the Joker and I do the same thing. So I just throwing it out there. Make sure we're okay. Elizabeth looks super excited. If what?
If somebody in here was really afraid, like really afraid of clowns.
Then I'm helping you face your fear. Therapy. Yes, there you go. We at school, we're here to help you grow and become better people, and there you go.
Socio-emotional learning.
Yes, there you go. If you want to swim, get in the water. There you go. All right. So we have our focus activity. I do on Tuesday want to go ahead and have, I haven't decided yet if it's going to be a quiz or an exit ticket, probably a quiz, but one on Tuesday after we have our last focus activity for the grading period over correlation, because we just turned that in yesterday. If you do have any questions over that, please let me know. It was originally due today, but it's now due on Tuesday. What am I referring to? The linear regression. There we go. Okay, so linear regression. So we have a lot going on Tuesday, and then Wednesday, hopefully, we'll be able to continue just with the chi-squared test. And what is Thursday? Okay, we have our exam. So what's going to be on it? Everything. Okay, so what was the first topic we talked about after the previous exam? Cumulative frequency, standard deviation. What else? Normal distribution is a big one. Okay, remember, and I'm not really having you, I'm trying to remember, I don't think I'm having you do anything by hand. I think it's all calculator. I don't think I put a single table on there. I'll look into that and I'll let you know. But definitely know the keystrokes for how to go ahead and perform those operations. And then, we just continue. We're actually almost done with our statistics unit. And then after that, we're going to move on into sets and logic. All right. So let's see what our focus activity says right here. Number 1, a sample of 10 measurements has a mean of 15.7, and a sample of 20 measurements has a mean of 14.3. Excuse me. Find the mean of all 30 measurements. Okay, so how would I approach this problem? Somebody walk me through it. Okay, what do you think, Reese? Okay.
Would you multiply 15.7 times 10 and then add it?
There you go.
And divide that by 30?
Yeah, because we got 2 different averages here, right? So a sample of 10 measurements has a mean of 15.7. So let's say that whatever that sum is for the first set, when I divide it by 10, I should be able to get a mean of 15.7. And let's just say the sum for the other 20 measurements, let's say that's y. Okay, divided by 20, that was equal to 14.3. Yeah, so we need to know what the sum for both x and y is if we're going to find the average for the entire thing. So what is x represent? 10 times that 15.7. 157. Okay. And then here, we're going to have 286. There we go. So y is equal to 286. Now we know we're going to divide by 30 because I took the 10 elements with the 20 elements. So the grand total should be 157 plus 286, which gives me what? Okay. So divide that by 30, the total number of elements we now have. And what do I get from my answer? Okay. What'd you get, Joy? Oh. 14.8. Yes. Perfect. Okay, does anybody want me to show that in the calculator? Anybody? Radley? Oh, yeah. Tell me how you got it. I always like to hear the different strategies. Uh-huh. Okay. Perfect. I like that. Okay, nice. Did anybody else happen to do it differently? That's a great way of looking at it. Good. Okay. Well, let's see what's happened in number 2. Jana took 7 spelling tests, each with 12 words, but she could only find the results of 5 of them. These were 9, 5, 7, 9, and 10. So the way I read this problem originally, I'm guessing the score is the number of words that she spelled correctly. Okay. She asked her teacher for the other 2 results, and the teacher said that the mode of her scores was 9 and the mean was 8. Given that Jana knows her worst result was a 5, find the 2 missing results. Wouldn't that be great if somebody like asked me about a grade and I gave you a math problem instead? I agree, it would be funny. Okay, all right. So how would I do this problem? What's that?
That would scare us more than that, I guess.
Really? You know, it's kind of funny. You can tell who's kind of just desensitized to it. You know, the violence we have, and who's just like, no, you know. Nobody's cussed today. I'm kind of sad about that. Nobody's just gotten, nobody's punched me either, so that's good. I've only been punched once since I've been doing it. And the student is actually still here. Does anybody know James Latour?
No.
It was several years ago when I had him as a sophomore. He double punched me in the chest. And I mean, you can't fault him because you have the fight or flight response, right? He was just like, just like that. No. You're not saying anything against James. Okay. Just saying. But you'll notice when I walked in, I immediately changed what? My glasses, because I know if I'm going to put myself in that position, potentially it could happen. So see, I'm thinking. Probably not thinking very smartly, but I'm thinking. Okay. All right, so back to math. Okay, what do I do? Let's see. The information we have so far is that the mode is 9. That means 9 is the one that appears the most often, and we know the mean is 8. Okay, so maybe we could start there. So let's say we're missing these 2 values here. Let's do the same thing as we did before. Let's say the missing scores are just x and y. Okay, so x plus y plus... Now somebody give me a grand total of what we have here. The 5 that we know. 40. Okay, we're going to go ahead and divide them by, what do we have here? There were 7. Okay, and that's equal to, we had a mean of 8. So I know that x plus y plus 40 should equal 56. Okay, the equation that I created, all I did was multiply through by the common denominator. Okay, so I know that whatever the 2 missing scores are, their sum has to be what? Has to be 16. Okay. Now, it also helps me, in fact, if they didn't give me this last statement, there would actually be 2 possible answers. Okay, 2 ways for this to happen. But we are also told that she knows her worst result was a 5. So we don't have anything less than that. All right. Well, let's say if we were to go ahead and say one of the missing ones was a 5, just kind of like what if scenario. Okay. Well, what would the score on the other one be? Okay, remember it would have to be 11, right? But now, why is that not a possibility?
9 would no longer be.
9 is no longer the mode, okay, because we also have this repeating. All right, so that's out. So basically, I just kind of went through the few possibilities that we have, and I came up with the 2 scores. Can anybody tell me what they are? They are 7 and 9. 7 and 9. There we go. All right. And I'm sure there's a way to continue mathematically, but from there, once I knew the sum had to be 16, but the lowest score was 5, then I just started pairing up numbers that were going to give me that total and went from there. Kind of just crossed them off. Did anybody do anything differently? How many people had both of those answered before we started? Okay, a few hands. Okay, good. All right, now hang on to these. Remember, how many do you have right now? You got 3. You will get number 7 on Tuesday. Now, they're due Wednesday. If you want to turn them in on Tuesday, perfectly fine. Okay. Just a reminder, in 2 weeks, 2 weeks from today, what is it? The end of the first 6 weeks. Can you believe that? We're already 2 weeks out from the end of the first grading period. Okay. So we got a correlation quiz on Tuesday, focus activities on Wednesday, major exam next Thursday. So even though it's a short week, a lot of important items are going to be taking place. Okay. Well, let's keep going. Yes, ma'am. Yeah, you want to go right there? All right, so let me go ahead and get my notes out right here. There we go. Okay, so we started talking about the chi-square test for independence, and we definitely started to talk about it, but we haven't gotten everything that we need. Remember, this lesson's going to be progressive because I just don't want to go ahead and throw everything at you at once. Where we left off yesterday, I believe we went ahead and actually determined our first chi-squared value, but let's start at the beginning. Once you go ahead and collect data and go ahead and put it in a table such as this, which we call either a 2x2 or a contingency table, well, what do we refer to this data as? Okay, starts with an O. This is my observed frequency data. There we go. This is the data that you actually would collect, all right? Now, the one thing we started practicing yesterday, and I want to go ahead and continue to do so today, is to find what we call the expected frequency values. Okay, now, first off, let's go ahead and choose one of these. Let's say 103.68. Now, this is the exact same table, but these are different values than from the observed frequency value table that we were just looking at. So let's say 103.68. How did we get that number? What did we do yesterday to help me figure it out? Okay, there you go. Whatever cell you happen to be looking for the expected value, you take that column's total, in this case 192, you take that row's total, 216, okay, and that's why down here it's giving you this symbol. Does anybody know what that symbol means? The upside down capital U? That means the intersection. That's one thing we're going to talk about in the next unit. But if I were looking at the column in the same row, see, that cell is the intersection of the two. That's why it's doing that. So I go ahead and multiply those sums, and then I go ahead and divide by what? 400. I always go ahead and divide by the total number of elements or participants, whatever is involved in the study. Okay, and that's where I ended up with the 103.68. And then I would just go ahead and do the same thing around the other cells using their respective sums in that column and that row. All right. Any questions on how I get the expected frequency values? Okay. Let's see, then we went ahead and got into it in a little more detail. Now, this won't be as important, once we get into next week, because I'll actually have shown you how to determine this. But right now, if we end up with a very, very small chi-squared value, what's that going to tell me about my quantities? Would they be independent or would they not be independent? Okay, they'd be independent. Well, what does that mean? What does it mean if two quantities are independent? John Henry. There you go. One in no way influences the other. There's no relationship between the two. Okay. So on the other hand, if we go ahead and calculate a larger chi-squared value, well, then we're going to say they're not independent. Well, that's just the opposite of what we just said. That means that there will be some kind of relationship. Possibly one does, in fact, or maybe even causes the other. But what was it that I said yesterday we need to be very careful of? Even if we determine that they are not independent, what does chi-squared not tell me? Well, no. I mean, we already know that. Okay, but it doesn't tell me what the nature of the relationship is. Okay, that would be up to us to determine that. And if you're going to use it in your internal assessment, you would have to decide, okay, according to my analysis, I'm showing that they're not independent. There's some relationship there. So I believe it is this. Or maybe you'll use another mathematical strategy to kind of strengthen your argument. Okay? It won't tell you what the relationship is. It'll basically just say, something exists. There is some kind of relationship. All right. And here was my formula. So F naught, that little F sub 0, that's the observed data. F sub E, that is the expected data. So you take the sum of the squared differences between the two, and then you go ahead and divide it by that respective expected value. Okay. And then I believe we went through one table right here. And our first one we calculated to be 0.217. Okay, so we're going to get the opportunity to go ahead and do this again today, but let's practice one other concept before we do it. Okay. Construct an expected frequency table for the following contingency tables. All right, so one idea is that a person either likes or dislikes fish, okay, versus what? Likes or dislikes chicken. I have no idea what the observed data is. In order to find the expected data, the expected frequency, you don't use that data itself. All you need are the sum of the columns and the rows and the total number of participants you have. Okay, so this first one, would you like to go ahead and work this together or go ahead and do it individually? What do you guys think you want to do? Bless you. Okay, whoa, everybody's talking at once. I can't, it's hard for me to separate the voices. Flip a coin. Do you have a coin? Come up with a great idea, but you don't have a coin. Oh, he's looking in his wallet. Okay. Bless you. Nobody has a coin. Okay. You have a coin? Gum wrapper? We could flip it. I don't know what it would tell us. We have a coin?
Yes.
All right. There we go. Let me see that. Thank you so much. Ooh, she gave me a quarter too. Do I get to keep it?
Sure.
Hey, I'm a teacher. You don't go into education because it's don't go into education for the money. All right. Call it.
Oh,
Heads we work together.
What's that?
Heads we. I don't know.
Okay, so Reese says heads we work it together, tails we don't.
Is that what the?
It is tails.
Okay.
that's what I said.
So tails we don't. Okay, so let's try it individually. I'm gonna give you your quarter back.
Thank you.
Yeah.
I was like, I don't
How was math today? You supposed to took my quarter.
yesterday.
Was he trying to change your mind? I don't know. Change. I'm sorry, Emmy. I was talking over you. Were you making a joke?
It wasn't important.
It wasn't important. Okay.
No, I was just Coach Pep is an interesting person.
Oh, I love Coach Pep. I never get to see him anymore, though. All right, so I'll give you about a minute or two. Now, is anybody stuck? Is anybody not sure what it is that I'm asking you to do? Now, this is actually something that could potentially show up on your paper exams. The chi-squared is a really large concept that they like to go ahead and create questions about. And sometimes they go ahead and ask, given some observed data, what the expected frequency value is for a certain combination. Like they might phrase a question such as, what's the expected frequency value for a person who likes fish but dislikes chicken? Okay. And I've even seen some go ahead and ask it in such a way where they want you to describe verbally how you come to that value, not just giving the value itself. So there's a whole variety of ways that these concepts can appear on the paper exam. Okay. So I'm going to stop talking and let you do your thing. All of these in this top one should be coming out nicely. Is everybody about ready, or do we need a few more seconds? Okay. All right. So let's find the expected frequency value for the number of people who like chicken and like fish. Okay. So what two numbers will I multiply? There you go. So I'm looking at this cell right here. That's scary, Jacob. Hello. Hey. Cortland. There you go. All right. Okay, so I'm going to take 75, the total at the bottom of that column for that cell, times 60, the total at the end of the row for that particular cell, and I'm going to divide by 100, and I should be getting what? 45. That's my expected frequency value. Okay, you do not have to have the original data in order to get the expected. You just need the sums. So let's just go from left to right across. Mariah, can you tell me the expected frequency value for a person who likes fish and dislikes chicken? Okay, 30. Are you sure?
Oh, wait, no, sorry.
There, now this one's 30. There you go. So this one's 15. So I'll go ahead and put both of them. This one here would be 30. Okay. So for this one, dislikes chicken but likes fish, 25 times 60 divided by 100. For dislikes fish and likes chicken, 75 times 40 divided by 100. And who do I not normally talk to? Naya. Okay, what would you say for the expected frequency value? You okay, Jim? Okay. Dislikes fish and dislikes chicken. 10. There we go. 25 times 40 divided by 100. Perfect. Now, is anybody having trouble finding the expected values? Anybody confused by that? Okay. What do these mean? What do these tell us? How do we define the expected values yesterday? Anybody think they can tell me in their own words? Okay, it relates to the quantities. Okay, maybe you can finish this sentence for me. Okay, these are the values we would expect to get if liking fish and liking chicken were independent. If there was no relationship between the two, this is the number, the values we would expect to get. Okay, remember this is different from the observed. That's what's actually collected. Okay, is everybody okay with that? Okay. Did anybody go ahead and move on to the other one? Where we have junior, middle, and high school, and you either play a sport or you do not play a sport. Okay. Let's go ahead and do this one together. All right. So plays a sport in junior high. All right. So I want to use this. Use this again. So I'm going to multiply 58 times 165, divide by what? 250. So let's go ahead and say we round these to 2 decimal places. All right. Who can help me out? Lizzie, can you help me out with this one? I want the expected value for a person who plays a sport in junior high. So 58 times 165 divided by 250. Okay. And then we'll have everybody else start looking at the others because I'm going to go ahead and just start randomly calling folks. 38 point, there you go, 38.28. Perfect. Okay. Now, normally you would go ahead and create a brand new table and go ahead and recreate the columns and the rows. I'm not going to worry about doing that. I'm just going to superimpose the value. How about Jan? Can you help me out with the expected value if a person plays a sport in middle school? Okay, to 2 decimal places. Perfect. 56.76. Okay. Amani, what would you say is the expected value for a person who plays a sport in high school? Yes, ma'am. High school plays a sport. 16.4? I got something a little off, a little higher. Let's see, what two numbers are we going to multiply? Okay, so the total of the column times the total of the row divided by the total number of participants. Ooh, I still got a slightly different value. Okay, and that's okay. Anybody want to help her out? I'm getting 69.96. Is that what everybody else is getting? Okay. Does anybody want me to put any of these in a calculator to kind of show where I'm getting them from? Are we okay? All right. Okay. Well, Jaylee, can you help me with junior high for a person who does not play a sport? What's that expected value? Okay, well, like your honesty. Okay. Sarah Beth, can you help her out? Okay, we don't have calculators. All right, who can ask now? Lucas. Has not figured it out. Laura, do you have it? Yahtzee. 19 point. But you know how to do that's what we're looking for. Okay. 19.72. All right, so just to kind of move this along. For middle school who does not play a sport, the expected value, I've got 29.24. And then for high school who does not play a sport, 36.04 is what I got. Okay. Any questions? Is anybody having any trouble finding the expected frequency values? Okay. Pretty straightforward. Okay. All right. Well, let's go ahead. Let's try another example. Now, this one we're actually going to go ahead and calculate the chi-squared value. Okay, so consider this contingency table. So we're going to compare gender to passing or not passing a math test. Okay, and I want to go ahead and throw out a disclaimer at the beginning. This is not my problem. I did not create this. I believe that whether you are a male or a female, you are perfectly fine to pass or fail a math test, okay? Mr. West is woke. Or I try to be. All right. So, having said that, now let's look at the problem. Construct an expected frequency table. So, again, I'm not going to worry about creating another 2x2 table. We'll just go ahead and superimpose the values. I'll do them in red this time. In fact, to make things go a little faster, you should get 30, 30, 20, and 20 for your expected frequency values. Okay. Anybody want me to go over where any of those came from? Okay. So interpret the value in the top left corner of the expected frequency table. And a lot of times they will have you verbalize, your thoughts. So in the top left corner, so it looks like males who pass a math test. How can we make that into a sentence? Like, remember, what did we just say the expected frequency values represent? If they're both independent, okay. So let's start to put that together. Now, what are independent? Okay. Okay. All right. So specifically here, because it said in the top left corner, we're looking at this number. So what are we comparing? Males and passing the math test. So 30 is the value we would expect to get if gender and passing the test was independent. Okay, is everybody okay with that? Questions? And I mean, is that the only way you could phrase it? Absolutely not. Okay, but it's the idea that you're trying to get across. All right, C, calculate chi-squared by copying and completing this table. Well, it's already been copied, not completed, but it's copied for us. Okay, so you'll notice the observed data is right here. 24, 26, 36, 14, the numbers that we were originally given. Now, the only thing is make sure that you put the expected value with its corresponding observed. Like, what would I put next to 24? Okay, 30. Next to 26 would be 20. Then we have another 30, and then I got another 20 here. Okay. All right. So again, it's a pretty simple formula to use, and I think a table does a great job of kind of organizing all that information for me. So now let's take the observed value and subtract the expected. So 24 minus 30. Negative 6. 26 minus 20. 36 minus 30. 14 minus 20. Negative 6. There we go. And remember, a lot of times if you do look at the values as you go through a table, you will notice patterns. Okay, that's going to happen a lot with your chi-squared test for independence. So now I want to square those differences, but these are all what? 36. So 36, 36, 36, 36. Okay. And then this last one, I want to take the square difference and divide by that respective expected value. Okay. So this is where I'm going to get a bunch of different numbers. So the first thing, I need 36 divided by 30. 1.2. Then 36 divided by 20. 1.8. And we already know that one, 1.2 and 1.8. So it's this final column where we have the full formula. Once I find the total, then I'm going to know exactly what my chi-squared calculated value is. What is that? It is 6. Now, compared to the problem we did yesterday, we got a really small number. I believe it was somewhere like 0.217. So because it was really small, we said that those quantities were independent, right? Well, how does 6 compare to 0.217? Okay, it's much larger, right? Okay, so with this being a much larger value, what can we say about gender and passing math? Would you say independent or not independent? Yeah, I mean, there's a correct woke answer, but I'm talking about the data. Okay, that's why I put the disclaimer in front. Oh, okay, I thought you were, okay. Yeah, so this one, because 6 is so much larger than 0.217, we would go ahead and say they are not independent. There is some kind of relationship there. According to this, not Mr. West. Okay. Mr. West, whoa. All right. Let's see, is anybody thinking about the same question that we brought up yesterday? What was the question that we talked about at the very end yesterday? How do you know where the line is? When does the number become too large that they are suddenly going to have a relationship with each other? Okay, so see, we got to get the basic ideas down before we start looking at that. Anybody have any questions about actually performing the chi-squared calculation, the expected values, any of our terminologies? Anybody lost? Okay. All right. Well, now let's push into the next part of this. Okay. And we'll just see how far we can get. We got what, maybe 10 minutes? Okay. So the formal test for independence. We have seen that a small value of chi-squared indicates that the two variables are independent, while a large value of chi-squared indicates that the variables are not. Okay, but the question is, at what point does it change from independent to not being independent? Okay. Now, there are two things that this is going to depend on. Okay. One, go ahead and highlight this. Okay. It's going to be the size of the contingency table measured in degrees of freedom and the significance level used. Okay. Those are two crucial aspects that's going to help you decide where that change occurs, how small or how large the value needs to be. Okay, in a contingency table, the number of degrees of freedom, now they'll always abbreviate it DF, degrees of freedom, is the number of values which are free to vary. Okay, so let me explain what this means. There's a formula to find this. Now, when you're trying to calculate the number of degrees of freedom, you're going to take the number of rows minus 1 times the number of columns minus 1. Okay, so let's say we have a 2x2 contingency table. Let's go ahead and figure out what the degrees of freedom are going to be. Okay, well, I'm actually calling it a 2x2, so how many rows do we have? We have 1, 2. Now, we don't include the sum row or the sum column. Okay, we only look at the rows and columns that contain my data. So that's why this is a 2x2. Okay, well, there are 2 rows minus 1 times how many columns are there? 2 minus 1, well, that's 1 times 1, so the degree of freedom is only 1. Okay. Now what this means is that when I have a contingency table with a DF of 1, only one value can be whatever it wants. As soon as that one value is chosen, the others are chosen. Let me show you what I mean. Now you'll notice these cells right here are going to be empty, right? So it doesn't matter. Give me a number you think will fit in B sub 1, A sub 1, this cell right here. Okay, I heard 7. Okay. See, we could choose any number we want as long as it fits with our sums. Of course, it would have to be less than 15 and less than 12. Okay. But see, here's the thing. As soon as I choose that one, that's the only free choice I have. Can I choose whatever value I want for B sub 1, A sub 2? Can I put any number in there that I want? Why not? There you go. Because we already know what the total has to be. See, that's what I'm referring to. You can only have one cell that can be any value you want it to be, within reason, of course, but then the others are chosen. Because if I go ahead and say, okay, this is 5, well, this 7 also determines this one right here. That would have to be 8. And this 5 also chooses this one, as well as the 8 choosing the other one. Okay? So going out of the way, there you go. That's what we're talking about when we say degrees of freedom. How many cells are free to be whatever value you want? Okay. Any questions on that? Okay. All right. Well, if we have a 3x3 contingency table, okay, it's just going to be the same idea. It's just larger. So if I have a 3x3, what they're doing here, see, they've got 3 rows by 3 columns. Remember, we never include the total row or the total column. We only look at the rows and columns that have data. Okay, so 3 minus 1 is 2 times 2. So that's how they got the 4 right there. So this one, we have a little more freedom. If we have 9 blanks to fill in, I could choose up to 4 cells. They could be anything I want, but starting with that 5th cell, the decision's already been made. Okay. Everybody okay with that? This is one of the factors that helps determine what your value is going to be if you're trying to decide, okay, well, how big does it have to be before independent becomes not independent? That's DF, degrees of freedom. Okay. Now this is the second part of that. As the chi-square value gets larger, it becomes increasingly unlikely that the variables involved are independent. Okay. But again, how large is too large? All right, the significance level indicates the minimum acceptable probability that the variables are independent. Now, we usually use either a 10%, 5%, or a 1% for the significance level. Now, a lot of times, you're going to be told what the significance level is. Okay, if you want your answer to be as exact as possible, okay, then you're going to go with 1%. Okay, so if your data is extremely important, maybe it's data relating to the medical field where it's directly affecting someone's life, you want your information to be as accurate as possible, right? So basically, as you move to the other percents, that's giving yourself a little bit of leeway. Okay, it's important to realize that, let's say I go ahead and determine a chi-squared calculated value at 5%. And it tells me that at 5%, my two quantities have no relationship. But I notice if I go ahead and move it to 10%, well, suddenly those two quantities do have a relationship. Okay, that's something that you can actually decide to do. All right, you get to decide which one it is. Now, in some problems, like on the paper exam, they're probably going to go ahead and tell you at 1%, 5%, or 10%. But if you're going to decide to use this on your internal assessment, you could choose any of the 3, okay? Even if it does or does not work with your topic. Now, personally, I kind of like to go with a 5% significance level because it's just like middle of the road, okay? It's somewhat specific, but not being overly specific. You see what I mean? 10% is definitely giving yourself the most leeway. Okay, well, this table of values right here, this is how you find the critical value, that one number. How do we know when the number gets too large? The question we've been asking. How do we know if it goes from being independent to not being independent? Okay, well, these are the values that we have to compare it to. So let's say you're working a problem, and you get a degree of freedom of 3, and you're wanting to do this at a 5% level. Can anybody tell me what the value would be I need to compare my calculated to on the chart? Let's see, here's 3. Here's the 5%. So the number that I calculate from my table, you remember that 6 and that 0.271 that we just calculated in the past couple of days? I would compare it to this number right here. Okay. Now here's the, yes ma'am.
If we were ever to see chi-squared on one of your tests
Mhm.
or quizzes, would you give us the significance of the table as well?
Actually, here's the thing. You do need to memorize that table. You know I'm messing with you, right?
It's Friday the 13th, so I figured.
Who said no? You know I'm messing with you, right? You do not have to memorize that table.
Well, I wasn't going to freak out, but I was going to ask questions, so that way I could freak out and
So let me repeat that. You do not have to have this table memorized. Okay? One of two things is going to happen like on my quizzes or a test. Either I'm going to provide the table on the exam, or I'm just going to go ahead and say, I want you to find me this chi-squared value, and here's the chi-squared critical. Now, these are what we call the critical. What we calculate by hand is what we compare to the critical. And unfortunately, I'm going to have to show you that on Tuesday. Okay, so this is going to be provided. In fact, 95% of the time, if a chi-squared question appears on your paper exam, they will tell you what value to use. Okay, but you'll notice I said 95% of the time. Did I say they would always give it to you? There's something else I haven't talked about yet that's going to help you figure it out, even if you don't have this number. Okay, so like I said, there's still a lot more information to go, but how are we doing so far? Is anybody lost? Okay. All right, so I'm going to go ahead and stop it there. I've got 206.